Geometry. First we draw the desirable fins with a specified diameter, length, and number. Then we draw a surrounding medium and extrude all the drawings. We apply boolean to subtract the fins from the surrounding. Keep in mind that the fins are chosen solid, and the surrounding is chosen as air. Afterwards we select all the parts and form one new part. Mesh. We select CFD and Fluent from Physics Preferences. Note that the minimum value of the orthogonal quality should be at least 0.05, and the maximum close to 1. Also the maximum value of the skewness should not exceed 0.98. Afterwards we create the following named selections by right-clicking on the specified faces: air inlet, air outlet, air base, fins base, and fins walls. Fluent. In the general setup we select pressure-based solver and steady-state conditions. We turn on the energy equation in models and select a specific viscous type. Then we choose the surrounding fluid to be incompressible ideal gas, and the solid to be aluminum from the materials option. In the boundary conditions, we choose the inlet velocity and temperature to be 2 meters per second and 300 Kelvin. However, we put an expected value for the outlet temperature since we do not know what will be the result. Then we specify the air base temperature to be 1000 Kelvin. Note that the fin walls should be coupled, which means the solver will get the solution for the temperature of the fins. Afterwards we select the temperature of the fins base to be same as the air base, which is 1000 Kelvin. In solution methods, we choose the scheme to be coupled, and the discrete ratio to be second order, to speed up the calculation. We then create monitors in order to see the variation of the static temperature on the outlet with iterations, along with the variation of static temperature at the fins walls with iterations. The solution is then initialized, and the calculation begins until the solution is converged after 99 iterations. Afterwards, we animate static temperature contours to visualize the temperature distribution along the fins. We can see that the temperature varies from maximum at the base, to minimum at the tips. Also the temperature is the lowest at the first row of fins, which are in direct contact with the cooled air inlet. Then we plot on the XY axis the temperature versus position curve for one specified fin. We create a line by specifying the initial coordinates of one point at the bottom, then the coordinates of another point varying along the z direction, which is the length of the fin. We can see that as we move along the length of the fin, the temperature will decrease accordingly until it reaches its minimum value. Then we write the data to a file in order to save the temperature versus position values in order to compare them with the numerical solution. Finally, by selecting fluxes in the reports option, we can find the total heat transfer in the fin's walls, which turned out to be 638 watts. Thank you.